So the index CP, the capability index, is defined as the variability allowed in the specification divided by the variability present in the process. The variability allowed in the specification, well, we have the upper spec limit minus the lower spec limit. The variability present in the process, we just went through, is 6 sigma. So CP is equal to the upper spec limit minus the lower spec limit over 6 sigma. And what this CP index is doing is then comparing these two. And we know that 99.73 of the process output is within these specifications. We compare if that is contained within the process process specifications. So if the CP value is less than 1, then the process variability is going to be larger than the variability allowed by the specifications. If CP is larger than 1, then the process variability is smaller than the variability allowed in the specifications. This means nearly all of the product will be within the specifications. And in general, the larger the value of CP, the better the process. Let's go through some examples. Okay, so here we have our random variable x, upper spec limit, lower spec limit, and the target in the center. CP is equal to upper spec limit minus lower spec limit over 6 sigma. So for example, if a CP is less than 1, with a centered process, we would see that the natural variation of the process, which is 6 sigma, is greater than the upper spec limit minus the lower spec limit. And in this case, we would have a CP less than 1, which means, of course, we have parts that are out of spec. For a CP equal to 1, this means that the distribution would be exactly within the spec. So 99.73% of your values would be contained exactly within the specification limits. And for CP greater than 1, the entire distribution would fall within the specification limits. And I can draw that like this. So here the 6 sigma value is smaller than the upper specification minus the lower specification limit. I hope that's clear. Because I'm going to give you now another example where we have two processes. They both have the same CP, but they look very different. In the first process, we have upper spec limit 64, lower spec limit 40. Distance between them 24. So USL minus LSL equals 24. And we have a process variation here. Overall, 6 sigma equals 18. So the CP is the upper spec limit minus the lower spec limit over 6 sigma. It's 224 over 18. This gives us a CP of 1.33, which is greater than 1, which means that all of our distribution here is contained within the spec limits. We even have a little extra. So this is good. But on this side, we have the same upper and lower spec limits. USL minus LSL still equals 24. And we have the same variability of our distribution. 6 sigma still equals 18. Our CP in this case is also 24 over 18 equals 1.33. But clearly you can see that there's a significant portion of the distribution falling above the upper spec limit. And why? Clearly because we are off center. Our process center no longer matches the target. Here's the target in these cases. Our process center is mu. So what does this tell us? The CP index is not able to recognize the lack of centering in the process, as it shows in B. It only compares the process variability with the spec variability. And customers normally stipulate that a CP should be at least 1.33. And this guarantees that the process variability is well within specification and allows for the fact that there may be some shift, some small shift of the process centering, and that this drifting around the target will not cause any of the distribution to go out of spec. CP equals 1.33 is meant to ensure that the product units will remain within specification even when there's some small change in the process mean. But from this example, we can see that the CP does not allow us to recognize the lack of centering in the process if the process is drifted, or drifted more than just a little bit. It only evaluates the process variability in comparison to the spec variability. So how to remedy this? We have another capability index called the CPK. CPK is defined as the distance between the process center and the nearest specification. So over half of the population variability. So to draw this out, again, upper spec limit, lower spec limit, target. What we're looking at is we have a distribution. Draw a distribution. Distribution has a process center, mu. This is the process center. And we are looking at the distance between mu and the two spec limits. Either the upper spec limit minus mu, which is here, or mu minus the lower spec limit. And we want to look at the one that's most critical. So in my picture here, we would have, this is the most critical. You take that value and you divide it by, before we had 6 sigma here, the entire distribution. Now we're looking at only 3 sigma, half the distribution. So we take the critical value, the critical distance, over 3 sigma. So here for the example, here's our target, lower spec limit and the upper spec limit. We have the distance from the process center to the lower spec limit and the distance to the upper spec limit. And here we see this is the distance to the nearest spec. And we would calculate then CPK is going to be equal to the upper spec limit minus the mean over 3 sigma. And in this case, because 3 sigma is greater than this critical distance, our CPK will be less than 1. Another example here, we also have a process that's off center. We have a process mean, we have a distance from the 2 specification limits. We see that this is the critical one, but the 3 sigma value is smaller than that critical dimension. So even though we're off center, we have such a well-controlled variability that our CP, which in this case would be mu minus the lower spec limit over 3 sigma, would still be greater than 1. But the CPK here is giving us the most critical value. So we need to make the point, though, before we do this example, is that both CP and CPK are population parameters, that like mean and standard deviation. We cannot know the exact value of the population parameters, but we're estimating them. We can estimate them from the sample data. Both CP and CPK, of course, need to have the estimate for the standard deviation. So if we take a sample to get an estimate of sigma, we can then calculate the point estimate of CP and CPK. And so we should just realize that a point estimate, like any point estimate, is just an observation of a statistic and is subject to sampling variability. And this means that different samples from the same population will give slightly different values of CP and CPK. And as your sample size gets larger, this estimate improves. So let's do one example together just to exercise this. A sample is taken from a process with a sample average equal to 41.5 and a sample standard deviation equal to 0.92. The specifications for the process are 39 and 47. What is CP and CPK for this process? So the first thing we do, we identify the parameters that we need. We have upper spec limit equals 47, lower spec limit equals 39. The upper spec limit minus the lower spec limit is going to be equal to then 8. Now, sample standard deviation, we use that as our estimate for sigma. So S is going to be our estimate for sigma is 0.92. CP is equal to the upper spec limit minus the lower spec limit over 6 sigma. So we have 8 over 6 times 0.92, which gives us 8 over 5.52, which is going to give us a very good value of 1.45. So looking at the CP, we think this looks very positive. We have a very capable process. It's greater than 1, greater than 1.33. Let's look at CPK. So the target is midway between the upper spec limit and the lower spec limit, which in this case is 43. But our centering, mu, the sample average, is equal to 41.5. So already we can see that there is some miscentering. So for the CPK, first we need to do the upper spec limit minus the process center mu. And for this we get 47 minus 41, 1.5, 5.5. And we look at mu minus the lower spec limit, which equals 41.5 minus 39, which gives us 2.5. So we need to identify for CPK the most critical, the minimum. So here we have, this is the most critical. CPK then is mu minus LSL over 3 sigma, which is going to be 2.5 over 3 times 0.92 equals 2.5 over 2.76, which gives us a value of 0.91. So here we can see that although if we were centered, we would have our entire distribution contained within the spec limits. But as we are off center, we know that there are some values falling beyond the spec. And so if we could draw this, with a target of 43, and we are centered 41.5. Even though our overall 6 sigma is smaller than the upper spec limit minus the lower spec limit, because of the off-centering, we have a critical value here of LSL minus 3 sigma, LSL minus 3, sorry, which is smaller than the half of than 3 sigma, which is half of our variability. So this example shows you how these two parameters can be used together. We have a few final remarks on capability. CPK, you can say, is a superior index for measuring the capability of a process because it checks process centering as well as process variability. But often these two, CP and CPK, are used together to make a comparison. This comparison then will reveal the condition of the process with respect to its variability and its centering and help in determining what needs to be done to improve the process capability. These indices are also used to track the capability of processes over time, to prioritize the processes for improvement projects, and to certify, for example, suppliers' processes or new processes. But it's also important at this point to take note of some of the shortcomings of these indices. One of them relates to the fact that we need to assume normality for our process. The 6 sigma in the denominator of the formula for CP is used to quantify the variability in the process, and this sigma is a characteristic of the normal distribution. When the normal distribution assumption does not hold, when the variable has a different distribution, if we evaluate the process's capability using CP or CPK, we can come to some serious errors or misinterpretation. And there are other methods then recommended for this. Another issue with these indices is that they can only be used when there are two-sided specifications. What I mean by that then is we have an upper spec limit and a lower spec limit. In our case too, we have then a centered target. There are other specifications then that are only one-sided and be thinking that when it's larger it's better or smaller it's better. And in this case, a CP and CPK are also not suitable because if something is extending out of specification on one of the sides and you don't mind, then it doesn't make sense to have a low CP or CPK. Another drawback is that the loss then is considered only beyond the LSL and the USL. The CP-CPK measurements consider that as long as the distribution is within the two specification limits, there's no issue, no loss. But as soon as the distribution extends beyond the specification limits, there's an immediate high level of loss. And this can be not true. You can see a degradation as you move away from the target, or you can have less of a loss, not a complete reason for scrapping as soon as you go out of the specification limits. So all of these issues are discussed in more detail in our textbook if you're interested, and of course there's a lot of work on this. One final note though, people who are working or are interested in Six Sigma method, Motorola Six Sigma method, the capability indices are central to this method and for improving process quality.